Good morning, everyone. We are at the beginning of another week of virtual school. I wanted to just take a moment of your time before I start talking about today's lesson to give a happy birthday shout out to Nick Neal and Jim Drew. Um, Boys, I hope that we can celebrate come May 15th. So for this week's lesson, we're still talking about limits. We're focusing today on a special theorem, and the theorem is called the squeeze theorem. It's also been referred to as the sandwich theorem, although I personally have never used that. I prefer squeeze theorem because what it really does is it takes two functions, one below and one below and one above, and it squeezes a function in the middle so that we know what the limit is. And that's kind of the basics. It's a technique used to confirm that a limit of a function by comparison with two other functions that we already know or that the limit's pretty easy to take. So if you consider the idea that there's a function trapped between two functions on an interval, and you know the limit of the one lower and the one above, and it turns out they're all equal, then we can say the function in between is equal. I don't know if you guys remember in September when I was walking around with water bottles filled with M&Ms, and we would have done this activity too, except for we're not in school. So, and we probably will still do it in September, but for right now, we're going to just kind of gloss over the idea. But if you remember, I had you guys all guess. And some of you guessed there were 50 M&Ms in the bottle. Others guessed there were 1,000 when we first did this. And then we started to narrow down the window. Remember, I was removing those Post-it notes until we got to the place where we had an idea of how many M&Ms were in the bottle, plus or minus a few M&Ms. That's kind of the idea of squeeze theorem. So here's a graph for you to look at. By the way, this is on page 39 in your packet. And so if you're looking at this graph, there are three functions. The first function being, h is above all three of is the upper function, f of x here is the lower function, and g is that function that we squeezed in the middle. And so if we look at h, we know that the limit as we approach c is L. And then if we look at f, we know that the limit as we approach c from both sides is still L. If there's this function kind of in between, we then know that the limit of g is going to be the same. And that's what squeeze theorem says. So that's it graphically. An easy example of that would be example A on page 39. It says if f of x is between 1 and x squared plus 2x plus 2, find the limit as x approaches -1 of f of x. And so what we're looking at here is we have a function f caught between these two other functions. And so this is a constant, and that's a pretty easy limit for us to find. The limit as x approaches -1 of 1 is just going to be 1. And the limit as x approaches -1 of x squared plus 2x plus 2. It's a pretty easy limit too. We're going to use direct substitution here. We're going to get 1 minus 2 plus 2. I think this side also equals 1. And so if f is trapped between these two limits, we can say, therefore, by squeeze theorem, the limit as x approaches -1 of this function f that we don't really know too much about is going to be 1. And that's the overall view on squeeze theorem. So we have these two functions. We either find the limit or know the limit, and then we can kind of lock in what that in-between function is going to be. Okay, so question B. Here's another graph we see. And we see that there's this function h of x, that's the green line, is stuck between the e function and the ln function. And so once we see that, we kind of already know that the limit's going to be whatever their limits are. And so their limits, I approach from this side, is going to be 1, and this side is going to be 1. Let's take a look at the other side. Here's from the left, and here's from the right. And so it's pretty much guaranteed that whatever the limit is of the two functions in which it's encased in, that's what it's going to be. So how do you write that? So we first are going to consider as x is less than 1. If x is less than 1, what we see here is that the upper function is g of x, right? And then we have h of x in between. And just quite lower than that, we have f of x. But for x is greater than 1, we see that we got g of x is now smaller, right? It's lower, the blue one. And h of x, which is less than f of x. And so we still see, though, that it is squeezed between from both the left and the right. Okay, so therefore, by squeeze theorem, the limit as x approaches 1 of h of x equals 1. All right, I'm going to make you a second video. I got to change out the paper. This is going to be where you're going to find your assignment for today. What I would like you to do is make sure that you give me some feedback on this video. Make sure you like and comment, and then make sure you take all the notes. All right, stay tuned for part 2.